Okay, welcome to the third session. We're going to have an invited talk by Mohammad Mahmoody and then some contributor talks. So our next invited speaker is Mohammad. Mohammad did his PhD at Princeton University and then a postdoc at Cornell. He's an associate professor at the University of Virginia. I'm always a fan of his work in the theory of cryptography, from black box separations and the connections to complexity. And we are going to hear about his recent work on relations to machine learning.
Okay, thank you so much, Gilad, and all the organizers for inviting me and the kind words. So, as the title says, I'm going to talk about some connections between cryptography, in particular coin tossing protocols, and what is now called adversarially robust learning. And at the high level, so in one slide, the outline is essentially as follows. I'm going to start by being a little bit more formal about what problems in adversarial learning this talk is about, which is not exactly directly about privacy, but rather a abstract problem that can also be about privacy if you want, but it's typically considered more about robustness. But the way I will talk about it is an abstract version that you can kind of think about it in many specific settings. So it's going to be about data that is given to a computer, and the computer is supposed to learn from it. However, the data or food here is kind of poisonous, and if it's coming from several parties, maybe some of them are providing bad data. The key part of the talk is to see that this question has connections to coin tossing attacks in cryptography, and in particular, multi-party coin tossing scenarios where more than one person, a group of people want to agree on a random coin, and if they were in the same room, they could do it, but they are not, and they still want to be able to do it over the phone or the internet, and in fact, some of them might be not following the protocol. And if there is time, I will talk about some connections that the proof has with functional algorithmic versions of problems in analysis, in particular measure concentration. But probably most of the talk would be about the first two parts, and it's not going to be a lot of proofs, but rather definitions and reductions. So that's one thing to have in mind. If you think it's not clear at any point, I'll try to keep track of the questions. I have two monitors, but if I could, then hopefully the organizers would interrupt me if there was something that needed to be addressed. Also, just as a comment, this talk, as opposed to most of the applications of cryptography in making things secure, here is the opposite direction, that we are actually trying to learn from the attacks that are developed, or ideas that are developed in the context of attacks in cryptography. So I will start with the first part of the talk, in which I'm going to tell what exact problems in robust learning we're going to deal with. The reason that we are talking about something like this is that, or more people are talking about this, that machine learning has been quite successful and has entered many areas of our life. And even though it was not originally designed or intended to be dealing with adversarial settings, once there is enough motivation to manipulate the system at any stages, we need to take care of it. Otherwise, we will gonna deploy models or run algorithms that are presumably secure while there aren't. And the basic problem that we're gonna talk about is going to be about classification. Classification, goes back, the way I'm gonna define it goes back to Valiant's work, one of his many pioneer works initiated formally talking about what it means to learn from labeled data. So I'm going to quickly review that setting. It's a very simple setting, but it establishes the terms and the goals when there is no attack. And then we can talk about what happens if there is an attack. So think about the distribution D over some inputs. It could be some distribution over images, for example. So capital calligraphic X is the set of instances, and there is an unknown, potentially unknown distribution over the instances. And there is a way to label these instances according to some so-called concept function. Suppose the concept function is just Boolean, but it doesn't have to be. It could be more than that, labels. And as the first step of the learning process, we are given a bunch of labeled examples. Each example I'm going to denote by MI has two parts. The first part is this instance. It's sampled IID independently from the same distribution D. And all of them are labeled according to the concept function that we want to learn. And that's the job of the learner. The learner, we call it L or just learner, is supposed to take these examples and map them to a supposedly good hypothesis or model, different terms for the same thing, which we will denote by little h, which is a member of the set of all possible hypotheses, denoted by calligraphic h, which sometimes is the same set of concept functions, sometimes it's not. Might be the concept function is something more complicated that we want to learn with something simpler, or vice versa. And the goal is to basically learn with high probability, which means that this hypothesis h, hopefully with high probability, will have close to zero error, or the more standard term for it is risk. And the error is simply measured according to the same exact distribution D that has defined the sample that is generating the examples. Otherwise, as Shafi said, it might be even impossible to learn or very hard to do. But for this setting, it's, you have examples, you want to be correct over the same distribution. And now with a little bit more picture, we can put these two steps of the learning process on two sides of this slide. On the first side, you see the training step, in which we have n examples sampled according to the distribution and then labeled, given to the learner, and the learner outputs this hypothesis. And then in the test phase, we have this same distribution D generating an instance, which hopefully will be classified correctly. Okay, now that we see we have two major steps in this process of learning and testing, you can imagine that each of these steps might be under attack. And indeed, many papers have studied each of these class of attacks. And I'm going to now just recall what they are called and what they're going to look like. The attacks on the learning pipeline, as I said, it could be done in the first phase of training or the test phase. We are going to deal with the training step mostly in the talk. Actually, I'm just going to focus on that, in which it is called a poisoning attack. So poisoning attacks, in fact, interestingly, if you trace it back again, it is another paper of Valiant that essentially started this line of work, and then followed by works of Kearns and Lee, and then Beshuti, Yaron, and Kushilevitz. And in fact, the last work of Beshuti et al. Is more closely capturing what I mean by the power of an attacker in this context. So it's the same thing as before. There is no attacker so far. There are n examples sampled, M1 till Mn. And then before we give these examples to a learner, an adversary who might get to see everything gets to change some of these examples and substitute them with malicious data. And then this new data set, which is a mixture of the good examples and bad examples, is given to this learning algorithm. And the learning algorithm is supposed to still output something that hopefully has a small risk. So this is the big picture of what a poisoning attack is. You can think about it in many slightly different settings where, for example, the examples are divided into batches, and the batches come from different sources, and then we're going to corrupt some of the sources. But for the talk, it's simpler to think about it as just a simple picture where we have a bunch of examples, and then only a limited number of these examples are going to be manipulated or tampered with. And still, we hope that the learning guy would do a good job. This is not, I'm going to specialize these attacks to a little bit more specific setting and tell you exactly what the goal of the attacker is. But this is the big picture of what a poisoning attack looks like. And it's a good term because if you, as I said, if you think about it, the training data as food, it's now poisonous. the type of attacks that I'm not going to talk about, and Xiaoqi pointed out those attacks in her talk, are also very popular. They're more known as adversarial examples in which the attack happens in the test time. So the attacker is not manipulating the training set, it's just changing the test example. And the hope is to kind of prevent the manipulated point to be misclassified. But we're going to focus on the poisoning story for the rest of the talk. And in fact, I'm going to focus on what is called a targeted poisoning attack. And this slide is going to be formally telling exactly what is the attacker's goal and limitations and so on. So think about the learning process starting with generating n data, n examples. Xi is again sampled according to the distribution D. All of these examples are labeled. And then, as we said, some attacker who gets to see everything might change some of these examples to arbitrary examples. And then they're going to be given to a learner. Now, what is the goal of the attacker in this talk? The goal of the attacker that you should think about is that it wants to increase the probability of some bad events happening over the hypothesis. So this hypothesis that is produced here is no longer produced under normal conditions. The attacker wants to make it far from normal with a very specific goal. So some event B is defined over the space of hypotheses, and the attacker's goal is to increase the probability that this hypothesis H tilde ends up having that property. And I don't denote it by H tilde just to point out that this H is no longer produced under the normal conditions. Tilde is referring to the fact that there's some attack going on. And you can formally define it by saying there is a subset of all possible hypotheses that we can output, and the goal of the attacker is to make learner output something in that set. And I want to emphasize that this definition, which is a very kind of core definition of this talk, because this is going to define what we mean by an attack on a learner, is pretty general, and it can be instantiating many specific interesting scenarios. For example, think about a learning process that produces a hypothesis, and I, as an attacker, have an interest to make this hypothesis output a very specific label later on for a specific test input. For example, I'm going to apply for a loan. This is a huge loan, and I'm a bank, and I want the agency who is going to, I'm not the bank, I'm a businessman, and I want to influence the bank's decision. And I want to do it indirectly by influencing the model that they will later on use to decide to whether or not to give me a loan. So this targeted poisoning scenario can model very specific targeted goals that are defined by a Boolean property. And you can also think about it as some form of privacy attack, that the goal of the attacker is to somehow leak some secret information that is observable in the training set, but is not supposed to carry over to the hypothesis. I'm not going to get into a specific context of either. I'm going to keep the problem kind of abstract. You can think about it to find applications for it. But interestingly, the history of this work and how these connections between poisoning and cryptography coin tossing attacks were established actually dates back to a TCC paper, and even before that, the crypto paper, in which the main goal was to harm privacy. But the way that the privacy is harmed essentially is through this abstract way, that there is this attacker who gets to see things behind the door. Think about it as a virus, for example, and it doesn't want to change the learning algorithm. It just wants to change, for example, some data before the learner algorithm gets to the play, and it wants to make this hypothesis have some property, and that property could be a way to signal some secret information, like 1 beta information, to an outsider. But for now, think about it more like a down to earth or something simpler to imagine that this H tilde would be a bad hypothesis if it makes a mistake on a specific point, for example, like a loan application. And I want to emphasize that this targeted poisoning setting is different from a big line of work on poisoning whose goal is to increase or control the increase of an attacker that wants to increase the overall risk of the hypothesis. So in this case, we are not caring about the overall error of H tilde. We're just caring about the specific property B that we want to make to happen. So if there is any question about this definition, it's a good time to take it, because if this slide is clear, it would be very helpful for many other things that we're gonna see in this talk. In particular, the connection to coin tossing would be much easier to see. Okay, so now the main questions that somebody can think about is like, what is really the best learning algorithm for this specific task under these attacks? I want to point out that if you really want to get to the core of what is the best robust learning algorithm, it's an equivalent question to ask what is the best attack, because it's a game between, eventually it's a game between a learning algorithm and an attacker. And if we can understand what is the best possible attack, we would also understand what is the best possible learning algorithm. So it has a merit to understand what is potentially an unavoidable attack, or in what settings certain attacks are enabled. And that's how we're gonna study this question. We're gonna ask what inherent or universal reasons would enable some targeted poisoning attacks. Under what conditions can we kind of design generic poisoning attacks? And lessons from cryptography, not technical lessons, but rather high-level lessons, is that it's a good idea. In fact, it's a very successful idea to cryptography to model the attack as a polynomial entity, because if there is an exponential time attack, it might not really affect the practice. We don't care about exponential time attacks necessarily in crypto. Even though we have information theoretic cryptography, the ultimate goal is to be just secure in real world, and those are technical tools that we use for this goal. Eventually, the real issue is to deal with computationally bounded attackers. And it's also a good point to say that it's not really that important to compute the polynomial time of the attack as opposed to the polynomial time of the learner, or the algorithms that we use as good guys, because the learning algorithm we're going to deploy, the attack is something that we are obsessed with. We are not necessarily going to implement the attack when we are designing algorithms. If we see an attack that is like n to the 10 or n to the 20, the history tells us that the attack might eventually end up with some small polynomial as well. And another direct message or implication would be that we can no longer base the security of our scheme on computationally hard problems. If we have a polynomial time attack on learning algorithms in some settings, it means that that setting couldn't be computationally secure by a reduction to, say, factoring being hard. So there are reasons that we focus on polynomial time adversaries. And actually this I want to emphasize, because this is not really common in the learning community, because this is more a standard in cryptography community, but we have tried to kind of make this point that things might change once you focus on polynomial time attackers, even in learning contexts. And we have some papers that do some separations of that flavor, but in this talk, I'm gonna just focus on polynomial time attacks. And another message from cryptography is that the main bad events that we want to prevent would be the ones that are hopefully going to be, so we want to prevent them from happening with non-negligible probability. So whatever happens with negligible probability, we can ignore. So with this picture in mind, I'm going to now describe the theorem that is influenced by this perspective, and is going to tell us something about the power of poisoning attacks in a generic sense, regardless of what learning algorithm is doing. So what we can show is that this is now the main theorem in the first part of the talk, that says for any deterministic learning algorithm, and this is a key point, if the learning algorithm is deterministic, then no matter what bad property you have in mind as an attacker, as long as that property happens with some non-negligible probability, there is always an attack that would amplify this bad probability to close to 1 by changing only a sublinear number of examples. And sublinear in particular, we are dealing with root n number of examples. So the learning algorithm was using n labeled example, and it had an original vulnerability of happening with non-negligible probability. If it was negligible, we wouldn't care. So the probability of that bad event is a very, very small probability, like 1 over n to the 10, for example. And the attacker now wants that probability of bad events to happen with close to 1. So it wants to make it like half or 75% or even close to 1. The theorem says it's always possible to do it. With some details that need to be clarified. For example, what I mean by polynomial time. Of course, polynomial time means that attackers should run in time that is polynomial in its input, but there is more subtle aspects to it, like what does the adversary have access to? It's also important that I'm going to comment on. So in picture, so it's the same picture that we saw before. There is a learner. There are n examples given to that learner, and the theorem says there's always a way to choose these adversarial locations so that this number of locations is just root n, and the hypothesis that is produced now is bad with very high probability. So for example, if it had a chance of making a label on a point with like probability 1%, now it's 99% over the randomness of the process. And some comments for clarification. What does this adversary need to run in polynomial time? Technically speaking, the adversary needs to have access to more fresh samples from the training distribution. So think about it, a bigger data set. For example, if it's about image classification, adversary needs a lot more images that are classified correctly, which might be available, or you can sometimes in some contexts, you can even generate them using generative models and so on, but that's technically speaking what it needs. And some extra properties that this attack has, which is not in this theorem, is that the attack is online in the sense that it doesn't know the future examples. It just knows the examples so far, and it's something that the learning community evidently cares. And what is probably the second property that is more surprising and it's interesting is that this attack doesn't even use wrong labels. So this attack still uses correctly labeled examples, and it would amplify the probability of that bad event B happening over the hypothesis. And the term that we have used in our paper was correct label. Evidently, the more common term in learning literature is clean label. But if you Google both, you see that there are many poisoning attacks that are trying to be clean label. And it's interesting that something like that happened. So you might be surprised that why could even something like that be possible. The thing is that the attacker at the high level tries to find, so we already know that the learning process is not perfect. There is a chance that something bad is going to happen. So the attacker tries to push the learning algorithm to go into that bad direction by still using correctly labeled data that is bad for this particular learning strategy. So it's not completely surprising, but the fact that something like that is possible in a universal way might be surprising. So this is the main result about the targeted poisoning attack. And I'm going to eventually show you how to derive it from a coin tossing attack, which the reduction is not that hard, but the interesting thing is to actually how to get those poisoning, how to get those coin tossing attacks. Okay, so at a very high level, the proof is by reduction. I want to design a coin tossing protocol that if I can attack it, I would be able to attack this learning process and end up increasing the probability of this bad property defined over the hypothesis. So to begin with, like any reduction, we will say, okay, I have a learning process. This learning algorithm is what I want to attack. And there is this data set, M1 till Mn, that I'm giving to this learner, and it produces this hypothesis H. Now we're going to define a coin tossing protocol that is defined based on this learning process in a very simple way. I'm going to interpret the ith example as the ith message that is being sent by some party that I call PI. So just pretend that MI is a cryptographic message coming from party PI, and there are n parties totally, and they want to agree on a bit, final bit. Well, if I say that MI is a message coming from PI, how can I define the final bit? Well, the learning algorithm defines the hypothesis, and then we look at this hypothesis. If that hypothesis has that property B, I will call the output to be 1. If it doesn't have that property B, the output is 0. So the learning algorithm implicitly is defining one bit. Why? Because there is this event B defined over this hypothesis. So if B happens, we say the output is 1. If B doesn't happen, we say the output is 0. So what is really happening is that you have n sources of data being aggregated, and then there is a Boolean function defined over them. And you already know that that Boolean function has a chance of being 1. You want to increase and amplify that probability to be 1. So this is something that you can also see as a special case of coin tossing. The benefit is that once you do that, you can look at the coin tossing papers and you see techniques that are actually designed. You can put them together to show how to do this amplification. So if the coin tossing attack increases the probability of this bit B being 1, that automatically means that I'm doing the targeted poisoning. So now I'm going to be a little bit more specific and say exactly what type of coin tossing I need. You have already seen what I need because you know what my motivation is, but I want to be a little bit more formal because it helps us to state the theorems at the coin tossing setting and be kind of doing research in terms of what we really need and what can be done. So the coin tossing that we care is the following. As you saw, I'm going to define n parties because I already said that the ith example is coming from the ith party. And in my protocol, PI is sending a message MI. I'm going to even allow it to be interactive in the sense that I say, suppose the PI is sending the message MI in round I, and I can handle more broad class of coin tossing attacks than what I really need. But it's easier to think about things in an interactive sense because the proofs are actually easier to understand as a random process. Just because the proofs are more general, it's also easier to see them as a random process. So think about the following game, very simple coin tossing. The ith party is sending a single message in round I. So in this case, we have 5 parties. Each of them is sending a message. If you want to connect it to poisoning, each of these messages, for example, a batch of data. And these are together defining the final bit B. And this bit B is either 0 or 1 because it's a bit. And the question is, what if an adversary controls some of these parties? How can this adversary bias this output toward 1? So I want to emphasize that this is a coin tossing protocol that needs to be of specific form so that once we attack it, it would be able to translate to poisoning attack. You cannot pick an arbitrary coin tossing protocol. These aspects are important. First of all, the messages should be allowed to be longer than bits because I want these messages to model labeled examples. And the adversary wants to increase the probability of B. Typically in cryptography, we're okay if the attacker just biases towards 0 or toward 1. But in this context, we don't care about just doing it either way. We want to be able to choose the direction. So you can, without loss of generality, say that the adversary wants to bias it towards possibly both directions, or in my view, just towards 1. So these are equivalent. I will always want to increase it to 1, more likely to be 1, or I want to do it both ways. But typically in cryptography, if you pick a paper, it gives you an attack either way. And finally, we want the polynomial time attack. And all these things make a potential attack to a coin tossing harder, but still we want to be able to do it. And the computational model that we care to prove the coin tossing attack theorem is, so you can think about it a very simple world that all these messages come at the same time and then the attacker can see everything. But if you really want to attack in the interactive setting, the corruption model, technically speaking, would be what is called a strong adaptive corruption. And it means that the attacker in the round I has the luxury of deciding to corrupt that person or not after getting to see their messages. So suppose you are in round I, adversary can see what the message is to be about to be sent. So MI is the message that the ith party is about to send. And then the attacker can look at it, decide, should I corrupt this person or not? And if I don't corrupt that person, it doesn't count against the budget of the attacker. So this is something that makes the potential the attack easier to do. The interesting thing is that it's still okay for poisoning because, as we said, you know, the poisoning setting, we just look at everything. So the adversary actually gets to see everything before changing. So it's okay for that application. So pictorially, you can see that the second guy is corrupted after the message was selected. So attacker gets to see it. And then the third person adversary doesn't choose. The fourth person, it was about to send M4, Adversary chooses that person to corrupt it and then changes the message. And then the bit is finally defined. So the corruption model is technically this model, but you can think about it as just an offline setting that everything is visible. This is just a stronger theorem. So the theorem that we prove for coin tossing is exactly this. We say any coin tossing protocol of the form that I just defined, and namely messages are just one message every person, and the message are arbitrarily long, and the goal of the attacker is to increase the probability of B being equal to 1. What we show is that there is always a way to do it in polynomial time by corrupting only root n number of parties. So once you prove this, it's a very general setting that covers the learning as a simple special case, because as I said, just think about MI being the ith example. And then you get the theorem of the first part of the talk, boom, as a corollary. Okay, so if there's questions about what is the main result about the coin tossing, it's also a good time to ask, because these two are essentially the main two results. So I will so I want to comment on some related works. Some of them are very old works from 70s. So the thing is that the way I define the problem in both learning context and coin tossing, there is, if you don't care about the polynomial time aspect of the attack, and if you don't care about interaction, you can actually use known results from measure concentration to get the result. So from 74 all the way to 90s, there are many theorems proved in measure concentration. In particular, the version that I'm going to briefly talk about is by Talleyrand. All of them say that at the end, they say that if you don't care about the running time of the attack, and if the adversary gets to see all the messages before trying to choose which ones to corrupt, basically you can derive it from concentration of measure in product spaces under Hamming distance. What it says is that that event that happens with a small probability is going to expand pretty quickly to 99% once you look at the close neighbors that are obtained by tampering. So if you start from what you want to achieve, which is the probability B, that probability B, so that event that we call it property B is going to be close to almost all the points under small Hamming distance, which means under a small number of perturbations. The catch is that all those proofs are not algorithmic. They're just existential. So if you look at those proofs, they essentially inductively show that the measure is going to expand, and they don't tell you how to go back and find the tampering that you need. So what we really do is to give an algorithmic proof for these classical results, basically. So as a special case, we obtain algorithmic proofs that tell you how to find something when these results only tell you that they exist. So that's one thing to point as previous work. The other point is that, you know, works from 89 in the context of coin tossing, you can also see them as very related. For example, Lichtenstein and Lineal Sachs solved the problem for the bitwise case where these messages are just one bit. But that's not good for us because we want these messages to be training examples, so we cannot use that result. They do other things also well, but their attack is actually not even polynomial. And recent works of Kalai, Komorgotsky, and Raz, and more recently Heitner and Kerry Heller, shows how to solve the problem of long messages. So that's okay, you can have long messages, but they do not get an attack that always increases the probability of this event B. They can only show how to increase it or decrease it. And the attack is not polynomial time either. So the high level of the attack, I'm going to just have one slide to tell you what the attack looks like because there is no time to get into the analysis of it. The attack is very simple, and I want to emphasize that the attack, which is so simple, still gives corollaries of the form that you saw. Even if you don't care about learning, if you just want to care about, for example, Chernoff bound, essentially you can derive an algorithmic version of things like a MAC pyramid from this result. So it has many applications, including coin tossing and poisoning. So the attack is simple, and it's as follows. Suppose the messages that are sent so far are M1 till M-1, and they're finalized. So some of them are real messages, some of them are adversarial. An adversary gets to see the next message, which is MI. Adversary wants to decide, should I change this message MI to something else or not? And the goal of the attacker is to ultimately make the full transcript imply 1 or have some property that adversary has in mind. So the very natural strategy is that the adversary wants to know, is this MI already good or should I change it? And this knowledge is something that the adversary can leverage on and say, in retrospect, with the knowledge of M1 till MI and conditioned on M1 till MI, how much do I get to increase the probability of MI by changing it to something else? And the key point is that we do it in a technically a multiplicative influence way. So technically speaking, the attack says, suppose the expected value of having that property conditioned on the transcript so far is beta. And suppose if I change the last message to MI star, this expected value goes to beta star. Is there any such MI star that I can find such that the ratio between these two is slightly more than 1? So I have a slightly more than 1 multiplicative increase in my expected value of getting to 1. And this is a very simple attack is the analysis of it uses many ideas from a series of papers. But I want to point out that there is a reason that this attack is a good attack, is that if you could implement this attack efficiently, this would always guarantee to get to that property with probability 1. The catch is that we cannot really do this in polynomial time always. We have to approximate this attack. But if you could implement this attack, you would never get to 0, because if at any moment you were about to kind of get to a regime where the output is going to be 0, the adversary would definitely intervene and change it, because there would be at least one other message that would also have a chance to get to 1. So you would always have a chance to get to 1, which means that you would end up with 1. The problem is that this attack, as stated, is not polynomial time. However, this attack is polynomial time friendly. You can just repeat everything polynomial many times, approximate every number that I've written here, and then you end up with a probability close to 1 rather than 1. And the analysis is using some potential functions that are carefully chosen, so I'm not going to get to that. But the attack is very simple. So if you want to get a sense of what is the attacker going to do, this is what it's going to do. And because of the nature of the attack, we call it multiplicative conditional influence. So we use the tradition of systems paper to give a name to our attack, but I personally think it's not that a big deal. And there are other versions of the attack that use additive influence, but there are reasons that they don't work. They get stuck at some bound that we don't want to get stuck to. So I want to now just leave 5 minutes for questions, because the last part of the talk was optional. And I already point out in my talk the connection to algorithmic measure concentration. So because the slides are going to be also available, whoever wants to look at that extra dimension of the topic, you can always do that in the paper or the slides. But I'm not going to get into that, and just to summarize the talk and answer any possible questions. So to conclude, what we saw was a polynomial time attack on collective coin flipping, essentially, in a model that was carefully chosen to be able to get all these applications from it. In particular, what we could show is that you can get polynomial time targeted poisoning attacks against robustness of learners in a general abstract setting where there is this one property that you want to make it more likely to happen over the hypothesis. Whether that property is something that it indicates violation of correctness or violation of privacy, you can choose. But the point is that once you define that property, there is always a way to amplify it. And also, if you want to care about technicalities, it implies algorithmic questions. It actually defines many algorithmic questions for concentration bounds. You can ask questions about how to find things that probability theory tells you that they exist, kind of at the very, very high level, similar to algorithmic proofs of Lovász's local lemma, that we already know how things exist, but we didn't know how to find it. And for future work, I think there are many things to think about. For example, because this attack is very abstract, you can try to find more applications of it or see what problems can be cast as this one-bit attack that we know it exists. And other technical questions is how many samples do the attacker need to run this attack? As I already told you, this attack needs to have polynomially many samples more than the learning algorithm. Is it inherent, or if it is, how big of a data set does it need? So that's a question that you can ask in terms of computational concentration, again, by number of oracle calls to the sampler. And finally, as I said in the talk, this connection between coin tossing and learning, once you go into the reduction, it only tells you how to attack deterministic learning algorithms. So this is another manifestation that we all are so familiar with in crypto, differential privacy, all these topics, that randomness is crucial. So this is another place to say that, look, if your learning algorithm is deterministic, there is this inherent attack. Now, can we prove something positive that resists such attack by using the randomness? I don't know. So all I know is that my attack breaks, this attack breaks down, but I don't know how to defend it provably using randomness. So this is probably the most interesting thing. It points out that there is another venue to provably show the usefulness of randomness, but whether or not we can do it, I still don't know. So this is my talk, and I conclude, and I'm happy to take any question. Sorry that the number of minutes for questions is not as much as I wanted to.
Thank you very much, Mohammad. It's very interesting. We have one question from Rohit. Do you wanna? I can unmute him. And then...
Oh, so the question is actually about this comment that I just made. What are the barriers to generalizing this attack to beyond deterministic learners? So if you look at the reduction, so I can completely explain what the barrier is. If the reduction, the way it worked was that I interpreted every message of the learner as coming from a party. And then eventually I said, look, all the messages are coming from these end parties, and now my attacker wants to be able to potentially corrupt everybody, but only corrupts a few of them, but it might corrupt all of them. So if there was extra randomness, it would be not included in this reduction because my attacker might want to also touch that randomness, which means if your attacker was allowed to also corrupt some of the bits, not all, but some of the bits of the randomness that was used, the attacker still would go through. But we usually keep that kind of intact. We usually in cryptography say, you know, this randomness hopefully is taken care of. And even if I don't know who sends this message, I at least can guarantee that my message, my randomness is okay. So if you're okay with a guarantee on randomness, this reduction completely gets stuck. But if you allow like attacker to also touch that randomness, it actually works. But I find it not very convincing in that case. So probably there is a way to use subsampling or something, but I don't know how to prove it, to provably prevent the attack, not just show where it broke.
Thank you. Any other questions? We have one more question on the chat. Do you want to read it?
Are the connections to Boolean function sensitivity? Well, it definitely there is, because what I'm doing is basically proving a theorem about sensitivity of functions. But the thing is that if you don't look at it as a random process, if you just look at it as a function, then the problem is quite well studied in the context in functional analysis, because you know, it's exactly measure concentration basically, but not the measure concentration in the form of Chernoff bounds that we're used to. It's an equivalent form that cares about like a median rather than mean. But basically the problem is understood. Once we move to random processes and allow the coin tossing to be adaptive and kind of the protocol going to different direction, you need a new proof, which we do have. But the interesting part is to do it in polynomial time, which we do. And you can, as I said, you can interpret it as sensitivity type theorems that are proved by an algorithm that shows how things can be found rather than just showing that the sensitivity exists. I hope that answers the question. The complexity of the attack is actually in P, the way I described it. It's another question. It's asking, is attacker's computation complexity NP? Because the attacker guesses some data from all data to be changed. So my attacker needs fresh examples. So think about the coin tossing setting, because that's easier to explain. In the coin tossing setting, everybody is just sending one message. The attacker only needs to continue the rest of the protocol after some messages are sent in its head. And that's a task that you can do in polynomial time, because every other person I can just run in my head. If there were more complications in the protocol, I couldn't do it. But because it's a single turn, everybody just sends one message, I can do that. And it's just an NP, or it's just a P oracle. You don't need NP oracle. But if it was more complicated, probably you would be able to do it with NP oracle.
Okay, thank you very much, Mohammad. It was very interesting.
You're very welcome.
We are
for the time and invitation.
Thank you so much. We are continuing to the contributor talk session. Antigone?
Yeah, so we go to the next contributed talks, and actually we have Kersting. Kersting Bound is going to moderate the session. So Kersting, please go ahead.
Yeah, okay. Thanks to you too. So yeah, for the first talk of the session, there we would have MP2ML, where Hossein is gonna give the talk. Do we have, fantastic. So yeah, this is MP2ML, a mixed protocol machine learning framework for private inference, and it's work by Fabian, Boemer, Rosario, Cammarota, Demmler, Thomas Schneider, and Hossein Yalame. Hossein, are you ready?
Yeah, hi. It's my pleasure to be here and present our work, MP2ML framework. MP2ML is a software framework with the goal of providing data scientists the ability to perform private inference. And our focus is on usability, since data scientists are neither cryptographer nor security experts. MP2ML will help enable private machine learning as a service. And this work was joint work with Fabian and Ro from Intel, Daniel from Uni of Hamburg, and my advisor, Thomas Schneider from TU Darmstadt. Okay, as we know, over the past few decades, we have more and more computational power, and in response, we've started collecting more data on which to compute. And together, this big data and computational power have given rise to machine learning, and in particular, deep learning. But we know the data is risky, and the deep learning needs the data. And some companies are storing customer data, and they run the risk of the data breach, and they have some privacy law violations. And for this reason, privacy preserving services not only avoid the cost of data breaches, but also enable the entire new business model. And now we wanna solve this problem. What's the problem? Problem is deep learning requires data, and we have contradictions. Deep learning requires data, whereas privacy prevents its use. And here we have a framework for this question. First of all, we have a lot of framework for PPML. Here we can see a list of recent work published at top conferences that deal with privacy preserving machine learning. They are based on different cryptographic techniques and offer different functionalities. They use either exclusively homomorphic encryption or exclusively multi-party computation. And we have one exception, something like Gazelle and Delphi. They're using both HE and MPC in a hybrid scheme. Pure homomorphic encryption lack the support of non-polynomial activation function, and they use some approximation. And pure MPC solutions support non-polynomial activation at the cost of leaking the full model architecture, I mean the convolutional layer. But hybrid HE MPC provide the advantage of both of the HE and MPC together. And for this reason, the MP2ML is based on hybrid HE MPC. Okay, if you want to talk about previous work, they are incompatible with ML frameworks, most of them. They basically they are based on homomorphic encryption approximation for activation function. But in MP2ML, we have a user-friendly front-end in TensorFlow. We use mixed protocol from HE and MPC together, and we hide a structural convolutional layer via homomorphic encryption, and we securely evaluate the nonlinear ReLU activation function via MPC. And our implementation are open source. We have two gadgets, one gadget for convolution layer and one gadget for nonlinear layer. For convolutional layer, we use the ngraph HE. ngraph HE is the works from Intel the last year. They support the CKKS encryption and they use a SEAL encryption library, which is also open source. And they have a direct integration with ngraph TensorFlow, and for other popular frameworks such as PyTorch, you just have to convert the deep learning model to ngraph format before running it. But in ngraph HE, everything's done in HE. And when we use the homomorphic encryption, we have some limitation. The first limitation is efficient implementation exit only for a leveled HE scheme. And there we have some limitation in multiplication depths. And also in ngraph HE, they cannot support nonlinear layer. And for this, they use some client aided protocol. And they letting client decrypt the intermediate result. And this leaks the model parameters. We only use ngraph HE for convolutional layer. And for nonlinear layer, we use an MPC protocol in ABY to privately evaluate nonlinear layers, such as ReLU activations. And this distinguishes our framework from ngraph HE. And this figure illustrates our secure MPC ReLU computation. And the first step is to convert the ciphertext to MPC value, then evaluate the ReLU. And to evaluate the complete network, MP2ML compute linear layer using homomorphic encryption as ngraph HE, and this protocol for non-polynomial activation. And the encrypted final classification, send it to client for decryption. And for more details, you can read the paper about our gadgets. And here we have one question, how we can deploy a private DL. And for this question, we have several difficulties. The first of all, we have to redefine low-level operations, such as addition and multiplication. Here we have new data types. We have ciphertext, we have plain text, and as opposed to floating point numbers in the machine learning venue. And we have one solution, something like, we can either add HE library calls to the DL framework or add DL calls to a HE framework or MPC framework. But implementing either approach requires simultaneous expertise in cryptography, in DL, and software engineering. And it's a daunting task for having some private DL. But using MP2ML, it's incredibly easy to use a private DL. Thanks to the ngraph TensorFlow bridge, you just have to add a single import line to Python TensorFlow code. And here we have a source code for a server and client to execute pre-trained CryptoNets ReLU in MP2ML. And the only difference to native TensorFlow code is the import line. And this makes it extremely easy to use for data scientists. And here you can see our comparison with the previous works. And we know Chameleon and Secure NN use a semi-honest third party, which is a different setting from MP2ML, and they use weaker assumption. Zon binarize a network, which will reduce accuracy on larger data set and models. What happens? And CryptoNet and CryptoDL use approximation polynomial activation functions, and ngraph HE use client-aided model to compute a non-polynomial function and is not secure. And our privacy is stronger than CryptoFlow, the state-of-the-art work, because we hide the topology of linear layers. Sorry.
Okay. Hossein, you're done, or? Did we lose him? Okay, I guess we've lost I guess we've lost his connection or so. Maybe we should continue with the next talk and answer possible questions either Zulip or in the end of the session if we have time. Then the next talk would be by Amos. Amos, if you could try to share your screen.
Can you see it?
Yeah, looks good. Okay, the next talk is going to be by Amos Treiber about CryptoSPN expanding privacy-preserving machine learning beyond neural networks. So Amos, take it away.
Thank you for the introduction. This is joint work with Alejandro Molina and Kersting of the ML and AI lab at TU Darmstadt, and Kristian Weinert, Thomas Schneider, and myself of the Encrypto group at TU Darmstadt. And I'll be talking kind of in the same setting as the previous talk of private machine learning inference, but using a different kind of model named some product networks, or SPNs in short. And this is basically a paper that will appear at the European Conference of Artificial Intelligence in a few weeks. So I'll start by talking about the status quo of private ML inference. We are like in the setting where we have a client and a server. The client has its input usually a feature vector X, for example, of an image, and the server has its input a machine learning model M, and we want to perform private inference on it, meaning we throw this X and this M into this magic hat, and out comes, for example, a classification result, and the server learns nothing about the client input X, and the client learns nothing about the server's model. And the way this is usually implemented is by using techniques such as secure multi-party computation, or MPC. And the research challenge really has been scalability, because this introduces a lot of overhead. And in the past years, there's been lots of work that tried different optimizations, and there's really been a race going on for the fastest private neural network image classification, usually. And this has also sparked interest in other domains, because privacy is becoming much more important now due to the GDPR. However, the GDPR also makes new demands on the machine learning models themselves and requires them to be more culpable and even explainable. And this is an issue for the current landscape of PPML models, because they usually rely on decision trees, support vector machines, and neural networks, which have kind of troubles explaining their decisions. Some other drawbacks of the works are that usually there's some accuracy degradation due to scaling that is employed to make the whole thing much faster. And also for many prototypes, they're not really integrated into machine learning software, and therefore are not really usable. And this is what we wanted to fix in our work by expanding the PPML toolkit to more models with usable software. And the type of model that we want to take a look at is called some product network, or SPN in short. SPNs were introduced by Kuhn and Domingos in 2011 and are defined as rooted directed acyclic graphs. These are univariate distributions on the random variables x1 to xn, and on top of that we build alternating sum and product nodes. A sum node represents a mixture over the same variables and is defined as the weighted sum over its children. A product is defined as the product of its children and represents a factorization over independent variables. And then we just do a bottom-up evaluation of the SPN until we reach the root value, and this is the value of the SPN. And without going into too much details, this type of model gives us a lot of advantages. A big advantage is that it can indicate uncertainty, meaning it will show you some value that gives you an idea of how fit the model is to make a prediction, and this increases trust in the model. Furthermore, it can easily handle missing information and is considered to be at a sweet spot between expressivity and tractability, meaning that there's a wide range of queries that can be supported in tractable time. And these advantages have been leveraged by several applications, for instance, image completion, speech reconstruction, activity recognition, image segmentation, and perhaps surprisingly, it has recently made an impact for database management systems. And as you now see that more and more applications use SPNs, we also need to find a way to make them private, which is what we do in this work called CryptoSPN, where we provide privacy-preserving SPN inference. Our general approach is to use Yao's double circuit MPC protocol with full floating point subcircuits of Demmler et al. We have to rely on full floating point operations because the type of fixed point approximations you usually see in the private neural network literature are insufficient for the guarantees on exactness of probabilistic reasoning that you want to have when using SPNs. So our approach is that the client acts as evaluator, has as input the random variables x, the server acts as gabler, has as input the sum weights and the leaf distribution parameters, and we put the network structure into the ideal functionality of the double circuit, and therefore we obtain the inference result at the evaluator. And we compute everything in log2 space using the well-known log sum AXP trick. This not only avoids underflows, but it also gives us a much smaller double circuit. Still using this approach, we have some non-trivial challenges that we need to address. One is that we need to hide the training data. This is because the structure learning of the SPN is data dependent, and by putting it into the ideal functionality, we make it public, and therefore we might need some sensitive information. To avoid this, we use random and tensorized or RAD SPNs, where the structure is learned at random, and the performance is similar to regular SPNs, and therefore we can just use them without losing much. Still, if you cannot retrain your SPN to be a RAD SPN, we offer mitigation techniques that can hide the scope, which is the assignment of the leaves to the random variables. To do this, we use an operator selection network that is encoded inside the guided circuit. This introduces an additional server input file that maps the M leaves to the N random variables, and this hides this assignment and therefore the scope. We also, of course, need to hide the random variables and model parameters themselves. This is, of course, guaranteed by the definition of Yao's double circuit, but we offer some more lower level log2 space optimizations for.
Amos?
Yeah.
Can I stop you for a second? Your microphone is a bit problematic and really hard to understand. Is it possible if you could switch to another microphone?
Yeah, sure. Can you hear me now any better?
Yeah, fantastic.
Okay, sorry about that. What was that? Yeah, so for hiding the random variables and model parameters, this is of course given by the double circuit security guarantees, but we offer some lower level optimizations for certain distributions. In terms of efficiency, we are linear in the network size. And in terms of security, we offer a semi-honest implementation that can, of course, be extended to malicious security by known techniques. Another thing that you should keep in mind is what has already been talked about in this workshop is that the ideal functionality itself might leak some sensitive information about the model. And we consider the investigation of this for the case of SPNs as important future work. Yeah. So we also implemented CryptoSPN and directly integrated it with SPFlow, which is a functional library for handling SPNs. As a backend for the double circuit, we use the API framework of Demmler et al., which is an MPC framework coded in C++. And the goal was to make this usable by machine learning experts because they can just use an SPN instance as already known in SPFlow, and then call the CryptoSPN conversion functionality to obtain a price-specific executable that can then be used between the client and the server to perform private SPN inference. And the code is freely available as open source. We use this implementation to perform a broad evaluation on standard data sets. There's really a lot of them, so if you want all the details, you have to check out our paper. We're just giving some quick highlights here. And these are for the case of 32-bit precision in our local area networks on standard machines. So if we look at medium-sized SPNs, size of 10,000 to 45,000 edges, we have a setup phase of 2 to 7 minutes, and an online phase which can be performed once the inputs are known of 8 to 30 seconds. We also looked at a small SPN with 3,000 edges, and there we have a setup phase of half a minute and an online phase of 2.7 seconds. These were all RAD SPNs. We also took a look at a small SPN trained for the NIPS dataset and wanted to investigate the impact of this operator selection network. And there, if you compare the runtimes of a regular SPN evaluation and one with using a previous function network, you can see that the overhead is just minimal. The obvious question is, of course, how does this compare with the related work? And the answer is that you can't really compare SPNs and neural networks because they serve very different purposes. What we can do is compare them in terms of sophistication. In that regard, CryptoSPN is still very much in its infancy, and there's lots of optimizations that can still be deployed. We do the advantages of the model, which is, as I said, the uncertainty, dealing with missing information, its exclusivity, and also we have software that is usable by machine learning experts. So in conclusion, we have seen that the PPML toolkit needs to be expanded, and CryptoSPN is the first step in incorporating probabilistic graphical models such as SPNs. We implemented it and directly integrated it with SP4 from our expert use, and we performed a broad evaluation that shows that accurate and private SPN inference is possible in seconds. Still, there's lots of future work ahead, like investigating the feasibility of fixed point SPNs and also private SPN learning. For completeness sake, here are my resources, and before I finish, a very quick advertisement. We have open positions at the Encrypto group in Darmstadt, so if you're interested, just go to that URL. And with that, thank you for your attention, and I'm happy to take questions.
There are any questions, please write them in the chat. Just one quick question from my side. How much do you actually lose by having to approximate?
This is like more of a machine learning question because yeah, this like SPNs have this fundamental property of exactness, which you don't really have in a lot of other models. And the question how the impact of the impact of using approximations is not really clear. You can't really do, for example, if you do classification, you can just do accuracy. But SPNs are suitable for much more tasks where you can't just have like a percentage of how accurate it is, and therefore the impact is not really clear. It certainly also depends on the application.
Okay, great. Thanks. I don't see any other questions in the chat, so let's move on. Oh wait, there's one more question by Divya, which you might just take quickly. Are SPNs still a classification task, or is the final value important?
Yeah, the final value is very important. The basic property is that they encode the joint probability and not a conditional probability, and therefore they can be used for many more tasks than just a classification. But you can also use do classification tasks with them.
Okay, great. So then, yeah, thanks again, Amos, for your talk. Then let's move on to the next talk about algebraic computation with comparison, where Han-Jun Lee is going to give the talk. And the screen is already shared. Fantastic. So let's learn a bit about ACCO. So Han-Jun, take it away.
Okay, thank you. Hi, everyone. I'm Han-Jun Lee. Today, I'm presenting our work on ACCO, a secure multi-party computation engine for fixed-point arithmetic and also secure comparison. Oh, wait, sorry. Let me full screen. Yeah. So we work in the setting where n parties, each holding a private data set, wants to collaboratively train a machine learning model. And in the end, everyone learns the model, but no other information about their private data set is leaked, other than the model itself, of course. A typical application is bank fraud detection, where n banks, each holding private transaction records, want to collaboratively train a fraud detection model. And every bank will learn the model, but wants to keep their private records safe. Our system is built on top of an efficient MPC protocol from GSD20, which supports only addition and multiplication of field elements. We extend it to also support integer truncation so that we can do fixed point arithmetics without overflow and also secure comparison. We maintain the original security guarantee of GSD20. It's maliciously secure in the honest majority setting, and it's security with abort. Here's a table showing some previous work on the same scenario. Secure ML relies on the ABY framework for non-arithmetic functionalities, while other proposed custom protocols. Usually, custom native protocols are more efficient than directly using the ABY framework. Also, as shown in the table, Secure NN is only semi-honest, and Blaze works only for the special case of 3 parties. A recent work, Helen, and our system both support multi-party native non-arithmetic operations and maliciously secure. However, we're working in different security settings. So Helen is computationally secure in the dishonest majority setting, while ours is information theoretically secure in the honest majority setting. And our system achieves a significant speed up compared to Helen. So our starting points for secure comparison and truncation are the protocols from N07 and CH10. To summarize, they both reduce to comparing a bit decomposed random share R and a clear element C. So one of our optimization idea is to design a log round circuit for this, replacing the original constant round protocol. So while we are losing on round complexity, we gain by having much less multiplication during the protocol, hence communication complexity. And in our application where a 127-bit field is used, we only lose 2 more rounds. We have 2 more rounds than the constant protocol. So we're not losing much, but we gained a lot efficiency. So here is a brief summary of the circuit. The inputs are bit decomposition of the random share R, and also we can directly read off the bits from the clear element C. For each bit position I, we compute a pair of intermediate values. So UI computes the bit comparison result for position I, and VI computes the bit equality test. So if we multiply the first L minus I bits, it is testing whether the first previous L minus I bits are all equal, or at least one pair is different. So the final result, the comparison result, is equivalent to the bit comparison result for the first, the largest position, such that they are not equal. So the first bit that differs dictates the result. And the following formula on the screen computes this result. By regrouping this formula, we get a similar looking formula, but of only half the original length, and we can recurse log number of times to get the final result. That's the circuit. So to make the semi-honest protocols from N07 and the CH10 secure, maliciously secure, we integrate them into the MPC protocol from GSD20. One advantage of this is that all intermediate comparison and truncation results are not verified one by one, but all batch verified in the end of our protocol. Also note that truncation protocols such as the one from CH10 and also EGK20, they commonly require the input to be within a certain range. And in a malicious setting, we need to check the range through a secure comparison on itself. Otherwise, this protocol leaks information. We avoided the range check by using a random mask. And this is not free. We had some extra step in the protocol, but it's cheaper than a secure comparison. So with comparison and truncation, we can now compute the soft threshold function with fixed point arithmetic. We will use the threshold function when we train a lasso model in our experiment. And it's easy to verify that it can be implemented using 4 comparison and 2 multiplications. So we set up our experiment to match Helen so that we can fairly compare with their reported performance. We used 2 data set, one of which is the million song data set, and we run ADMM training to get a lasso regression model that predicts the releasing year. The data set has 90 features per sample. And we use 5 AWS instances spread into 2 regions. And we report the L2 and MAE errors in our paper. As shown in this mini table, both Helen and our system achieve similar accuracy to a baseline implementation in sklearn. So this is to show that we didn't lose much by using truncation in our protocol. We didn't lose much precision and didn't affect the training result much. And this also shows that we achieve similar results as Helen, but training on the same data set. Our running time is only 71 seconds, while Helen reported around 1.5 hours. So we achieved a significant speed up compared to Helen. That's it. Thank you.
Okay, great. Thanks for a nice talk. Are there questions from the audience to Hanjun? Okay, Marcel would like to see the references again.
Sorry, I will, yeah. Let me, is it shared? Okay.
Oh yeah, I think that was the next slide.
It's 2 slides for references.
Okay.
So this is the second, and this is the first.
Okay, Hossein asks if you have a comparison with Trident, which is a 4PC scheme.
No, I don't think so.
Okay. If there are not more questions, then I'd move over to the last talk of the session, which is by Jen Sun. Thanks again, Hanjun, for the talk. Jen, I hope I didn't mispronounce your name. Could you share your slides?
Sure. I'm sharing the slides. 1 second.
Okay, while Jen is setting up, so this talk is going to be about de-anonymizing text by fingerprinting language generation. And it's work by Jen, as well as Roy Schuster and Vitali Shmatikov. And great.
Can you see that?
Could you possibly make it full screen?
Yeah, I'm now doing that. Okay.
Fantastic. So Jen, take it away.
Okay, hello everyone. I'm Jen Sun from Cornell University. Today I'm going to present our paper, De-Anonymizing Text by Fingerprinting Language Generation. This is a joint work with Roy and Vitali from Cornell Tech. Let's start with auto-completion. Modern auto-completion applications are driven by text generation models. The users of the application input into the app, and the app uses ML model to predict the next possible word. Here's a graph that shows how the language model-based text generation works. The language model takes the user's context as input and outputs a probability list of all tokens in the dictionary. Then the language generation app picks a token based on its probability. We call it sampling. There are several ways to sample a token. Pure sampling draws the next word according to the probability list. And greedy sampling always selects the token with highest probability. Top K sampling first selects words corresponding to the top K highest value in the probability list and applies pure sampling to the set. Among those methods, pure sampling usually produces poor quality text. Greedy sampling results in a lack of language diversity. Okay, but nucleus sampling, also called top P sampling, is similar to top K sampling, but instead of choosing candidates based on ranks, it chooses the maximal set of top-ranked words such that the sum of their probability is less than some value p. Let's look at some example of nucleus sampling. Here's a top p sampling with p equals to 0.9. We can see that in the left figure, the distribution is flat. So the nucleus sampling selects a relatively large nucleus with 15 tokens. The sum of the probability is 0.9 here. And on the right figure, the distribution is there is a peak distribution. So nucleus sampling selects a relatively small nucleus with only 3 tokens. Compared to other sampling methods, nucleus sampling produces high quality, high diversity text. But notice that compared to other sampling methods that samples from a fixed set, nucleus sampling samples from a variable, smaller set whose size depends on the input. Okay, then we showed that how to fingerprint a nucleus sampling sequence. We first look at an example of the nucleus sizes generated by auto-completion. In this example, the user first input the word "this," you can see it here, and the auto-completion generates a nucleus with size 9,000. Then the user input the second word "contest" here, and the auto-completion generates another nucleus, and so on. We call the series of nucleus sizes a nucleus size series. We call it NSS here. And we conjecture that a nucleus size series of any English sequence is a fingerprint if the NSS is sufficiently variable. We use an analogy with statistical variance to compute the variability of an NSS. You can see the equation here. We conjecture, to validate our conjecture, we tested the Reddit dataset using 6 different subreddits. We found that from 42% to 78% of sequences have variable NSS, and NSS of a variable sequence is unique, which means that there's no neighbors within a certain radius. We call this radius uniqueness radius. You can find detailed analysis in our paper. Then we show that how a popular implementation of nucleus sampling leaks nucleus sizes. Algorithm 1 is the pseudocode of the implementation. You don't need to know the details of this code, but notice the line 14 and 15. There's a loop here whose number of iterations corresponds to corresponds to the nucleus size. So since nucleus size depends on the input text, this loop is actually an input-dependent execution path. So it can be exploited by microarchitectural side channels such as flush reload. Okay, here's a graph shows the overview of our attack. The victim inputs some text into the auto-completion and posts it to some public anonymous forums such as Reddit. And concurrently, the attacker measures the nucleus size series using a side channel and store the measured trace to some candidate trace database. Later, the attacker downloads some anonymous text from the internet and simulates the auto-completion process locally to generate the nucleus size series. Then the attacker matches against the candidate traces. If there's a match, the attacker can identify the author of that anonymous text. Here's some evaluation of our attack. We can see in the left figure that the unique radius grows faster than the upper bound of the measurement arrow. The analysis in our paper shows that the attack produced no false positives even in an open world setting. And the right figure shows that the attack recall is greater than 99% when the sequence has more than 1,900 words. We also proposed a mitigation to the problem. Instead of using a data-dependent loop, we can change it to a loop with fixed number of iterations, as we showed here. The figure on the right shows the evaluation of the mitigation. We can see that before the mitigation, the runtime of the sampling function has a relatively strong correlation with the nucleus size. But the correlation is much weaker after the mitigation. The overhead of the mitigation is negligible. It only has 1.15x average slowdown in the loop execution time, which translates to only 0.1% increase in the runtime of the sample sequence function. In conclusion, we point out that common building blocks of machine learning can leak information on model inputs due to uninformed programming practice. Then we show that in nucleus sampling-based language generation, the series of nucleus sizes is a unique fingerprint. We should also show that an attacker can infer the input text by measuring these fingerprints via a standard microarchitectural side channel. In the end, we propose the mitigation with negligible performance overhead. Thank you.
Thanks, Jen, for the interesting talk. Really interesting work. We have time for 1-2 quick questions. The first is by Jonathan Passarat-Ballenbach. And if anyone else also has a question, just please post it in the chat. And Jonathan asks, what's a typical sequence length, just to compare with your 1,900 result?
What's the typical length of the? So basically, a sequence can be a typical sequence can consists of more than one post on the forum. Basically, we can concatenate multiple posts in the in an anonymous forum from the same user chronically. So basically, we choose in our experiment we choose 3,000 word sequence, which is very common in our database.
Okay, Jonathan, I hope this answers your question. Quick one for me as well, which is, could you possibly guess, for example, the topic of, so could you guess something about the context with a shorter sequence? So let's say instead of trying to guess the actual overall sentence, like maybe guess more information about that one with less words?
So now we are using a very simple matching algorithm. We only measure the L2 distance between the fingerprint to the trace. So if we can use some machine learning model to learn the pattern between the trace and the fingerprint, I think we can use much smaller sequence to do the matching.
Okay, great. Thanks. As there are no more questions, thanks again to you, Janet, to all speakers of the session. If there are questions in particular to Hossein, whose talk was prematurely ended, please post them on the Zulip chat for this workshop. And with this, I'd like to hand it back to the organizers, Antigone and Gilad.
Great, Kersting. Thanks a lot. And at this point, I would like to thank all the committee members for all the help. So thanks a lot. So now we have the last session. So we're going to take a break for 10 minutes. And we need to join another link. Yeah, so you can find the link online. So see you there in 10 minutes. And again, I will repeat, if you leave this room, the chat will be deleted. Okay, see you soon.